this series. Today's topic is about laser in imaging and material processing. Today's session will enlighten us on the basic laser operations, characteristics of laser radiations, types of lasers, and laser application in many medical fields and daily lives, and very many other topics to be discussed. Well, today we have a faculty from Amrita Vishwa Vidyapeetham, Dr. M. Sivakumar. He is the professor of Department of Science in Physics from Amrita Vishwa Vidyapeetham, Coimbatore. So before getting into the session, if any of the participants have any queries, please type it in the chat box. Sivakumar sir, I welcome you to the session. Therefore, we can start the series. Over to you, sir.
Thank you. Thank you very much. So can I share my screen?
Yes, sir. Yes, sir.
So is it visible properly?
Yes, sir. It's visible, sir.
Yeah. Good evening to all. So I'm just happy to, to give this just little presentation about this basics of lasers and how the lasers are used for imaging and material processing applications. That's what my presentation. So to begin with, just let us see what is actually the outline of my presentation today. So I will give some introduction about this development of lasers, actually, how it started developing. And then in the laser, there are some processes like absorption, spontaneous emission, and stimulated emission. So these are the three fundamental processes which has to be understood to understand the laser. And then what is actually laser and some of the characteristics of lasers we are going to see, because those characteristics are responsible for several applications, for example. So that's what we are going to see. So this is just an outline of my talk, today's talk. So here, if you see in the last century, so these are the greatest inventions in the last century. So first is atomic energy, so there are atom bombs and how this nuclear energy can be useful in a productive way. That also we know that. So those things are developed in the last century. In addition, the semiconductor chips, how the semiconductors are very much useful. And then we have the computer, the development of laptops and other computers. And then finally, laser. Laser is also one of the application in the last century. If you see now in the present day, without laser, we can't do any research in materials, actually. Even in the nanoscience and nanotechnology, laser is very much essential. Even in our day-to-day life, we are using lasers very much. So that we are going to see, in due course. So these are the four people, actually. You can see the first one is Mayman in 1960, and Torrance and Prokhorov and Basso. So these are the people, they just received a Nobel Prize for the research in lasers. These are the very, famous physicists in terms of lasers. Without these names, you can't find anything, any studies in lasers. So in the introduction, just I will talk about this absorption, spontaneous emission, stimulated emission, and then the next part will be what is the requirement for producing laser, that is active medium, population inversion, and the resonator configuration. So let us see one by one. In the case of absorption, I think you know very well about the atoms and how the electrons are present in the atom. So in the center, that is the nucleus. So you can see here nucleus in the center, and then around this nucleus there are orbitals. So I think you know very well, those who studied atomic physics, a little bit atomic physics, sufficient to understand this. So you can this configuration can be represented in terms of energy levels like this. So the first means ground level, ground state is the equilibrium state, and then first exciter state, the next orbital E1, E2, and E3, something like that. So when you just go for higher energy levels, higher orbitals, this looks, the spacing between the energy levels are very close and it becomes a continuum. So these are how the energy levels are present in an atom actually, because we need to understand then only you can able to understand what is absorption, what is spontaneous emission, and what is stimulated emission. So the next one is absorption. So in the case of absorption, you can see that there are initially the electrons are in the ground level. Okay, initially in equilibrium condition in an atom, the electrons are in the ground level. That means we have to say that the atom is in the ground level. Suppose a photon, an incident photon. So it is actually a light is incident on this atom, and the energy, the frequency of this light is equivalent to the frequency difference, the energy difference between these two levels. Then what will happen? The electron in the ground state will absorb this energy and will go to the higher energy level. So because this energy difference is equal to the incoming energy, that is frequency of the incoming photon, that's what I have given a simple equation, that is nu is equal to EF minus EI divided by H. So EF is actually final energy level and EI is the initial energy level. So if this is not taking place, there is no absorption takes place, then the matrix becomes transparent, so the light will come out of the material. So this is what simple absorption. Then the next thing is spontaneous emission. So once the electron is absorbing energy and goes to the higher level, it cannot be there in a higher level forever because it is a non-equilibrium condition. So it has to come back to the ground level. Then only the equilibrium will be reached. So in order to come back, so suppose let us see, in this energy level diagram. So you can see the electrons are excited. It could be excited in 3 energy levels, the first one and the second one and the third one in the excited states. You can see that the electron will come to the next level by emitting a photon, which is equivalent, the energy of the photon is equivalent to the energy difference between these two levels. Similarly, when it comes to this level, it can jump to the next level by emitting another photon. The energy of that photon is equal to the energy difference between these two levels. Similarly, from this level, it can jump to the ground level. So like this, the photon means the electron will go to the ground level. So these kind of emission spontaneously, the electron in the excited level will be coming to the ground level. So this is called a spontaneous emission. Actually, because there is no triggering, no stimuli, nothing. So you are giving an input in the previous absorption. So it is absorbing energy and going to the excited level. And then spontaneously, it is coming back. It is coming back by emitting a photon of energy equal to the energy difference between these two levels. This is called spontaneous emission. So these are very normal processes that takes place in atoms actually when you irradiate the atoms with light. The third process is a very important process. It is actually stimulated emission. This is actually first understood by Einstein in 1917. So under certain conditions, what happens is the atoms will be, that is the electrons will be in the excited level and an instant photon which is having energy equal to the energy difference between those two levels can stimulate the electrons in the excited level to make the electron to go to the ground level. Okay, so that means the incident photon as well as the emitted photon. So this kind of emission is called stimulated emission. So the photon emitted due to stimulated emission and the photon which stimulates that electron from the excited level, or both are in phase with each other and both are having the same wavelength, same frequency, same energy. So this is the fundamental thing for laser action actually. Okay, so and also this photon travels in the same direction as the incident photon. That's what. So again, I'm repeating, in the case of stimulated emission, you know that the electrons are going to the excited level by absorption, and these electrons in the excited level, there are two ways it can come back. One is already we have seen, that is called spontaneous emission. The other way is, if suppose there is an incident photon having energy equal to the energy difference between the electrons in the exciter level and the ground level. This incident photon trigger or stimulate the electrons in the exciter level and makes that electron to go to the ground level. That means makes the atom to go to the ground level by emitting a photon of energy equal to the energy difference between those two levels. So that means obviously the stimulating photon as well as the stimulated photon both are having the same energy. So this is the concept of stimulated emission. So both the photons are in phase and they are coherent. That means the state of this photon will be the same. The two photons will be the same. And then these two photons will stimulate further electrons in the exciter level and make them to go to the ground level. So two photons create four photons and like that. So it will continue. Okay, so that's what called, amplification. So this actually first it was found by Einstein in 1917, actually the stimulated emission process. So the next thing is, so you can see here how this is actually a small animation. You can understand how this absorption takes place. So an incoming photon of energy HF is absorbed by this electron and goes to the exciter level E2. And in the second case, spontaneous emission, this electron in the exciter level coming spontaneously to the ground level by emitting a photon of energy, this one. And in the third case, if you see carefully, an incoming photon of energy HF stimulates the electrons in the exciter level so that the electron will go to the ground level by emitting another photon. So totally there are two photons that are in phase with each other. So this is what the absorption and emission process in general actually. So, but this is just an understanding of how the absorption and emission takes place. But the next thing is, if you just see that, how the laser is developed, the scientists Charles Townes and Arthur Shallow, they just, thought that the stimulated emission process can be amplified. That's what they found. They were thinking, because they were just speculating that if this process, the stimulated emission, can be amplified, so that if it can be amplified, so you can see that suppose if two photons can be converted into some 100 photons, so all the photons are in phase with each other and they are coherent with each other. So this was just proposed by these two scientists, and that's what they just coined the name laser. Laser, an acronym for light amplification by stimulated emission of radiation. That is, the stimulated emission process can be amplified. That's what they thought. So how it is amplified, we are going to see that. Okay, so that's what. Let us start with one photon which strikes an atom in the excited state and releases another photon. And we have two photons, and these two photons in turn may be incident to trigger two more atoms in the excited states and give rise to four photons and so on. So this is what the amplification process. How this amplification process can continue, that we are going to see, because we need another some device called resonator. So that means it's a kind of oscillator that we are going to see now. So the next thing is, this is just a schematic representation of this amplification process, how one photon becomes two photons and two becomes four, something like that. So you can see here how the process, because the thing is, it is very difficult to keep the atoms in the exciter level, because it will automatically go to the ground level, because it is a non-equilibrium condition. So it is, not necessarily it will emit another photon when it goes to the ground level. Sometimes it will emit energy in the form of heat also. That is also going to be possible. So we have to just choose that process and medium in such a way that this stimulating process can be amplified, so it will come out as a laser process. Okay, so now the first thing what they have done actually, this amplification was possible in the microwave region. Okay, so that's what they have just first, before invention of laser, they know the concept, the stimulated emission can be possible, but they never told that it could be in the visible region or microwave region or any region. So first they tried with the microwave region, microwave amplification by stimulated emission of radiation. That's what this Townes, that scientist, he devised this method to amplify this microwaves of 1 centimeter wavelength in 1951. Okay, so he demonstrated that using ammonia molecules in 1953, he experimentally demonstrated this was the first measure, that is microwave amplification by stimulated emission of radiation. This could be possible at that time. They have done experimentally using microwaves, but they were not actually sure about whether it can be done in the visible region or infrared region. They were not sure about it. Okay, so this is what the development. And then next, actually, this is actually some details about this measure, that is microwave amplification by stimulated emission of radiation. So the frequency of this microwave photons is 10 raised to 13 hertz, and energy, corresponding energy. And this energy is actually same order as that of energy of air molecules. So, so that means the population of the excited states, actually, if you just see that, the population of the excited states is comparable to that of the ground state at room temperature. Okay, so this is what happens in the case of measure. So they are very clear about the process. The mechanism is very clear. So we know that what is stimulated emission, and in the case of microwave region, so we can able to amplify that. Okay, so the next thing is laser. So in 1960, subsequently, by Theodor Maiman, actually, he generated a laser beam of wavelength 694 nanometer from a ruby rod. This is what the first laser that is in visible region. It is in red. That's what he did in 1960 by Theodor Maiman. So he was the one, developed the first laser. So let us see the details of that. So actually, if you see that paper, what he developed, it was rejected by some journals, and then later, they accepted in Nature journal, that is a very famous journal. So they accepted that paper in 1960. Okay, this was the thing happens when the first laser was developed. So how the laser system now? So in the case of, in order to understand the simulator emission process, we have seen there are two levels. Okay, and we understand what is absorption and what is spontaneous emission and what is stimulated emission. We have seen that, but that is theoretically we can say. But practically, if you see, as I said, once if you excite the atoms to the higher level, it is a non-equilibrium condition. It will spontaneously come to the ground level. But in order to produce laser is light amplification. The photons has to be amplified. So one photon has to be amplified to 1,000 photons. So in order to do that, at least this atom should be in the excited level for some more time. That is, but naturally it is not possible actually with two levels. So with two levels, the laser action cannot be possible. Okay, so that is why people were started thinking about 3 levels and 4 levels. So that process is called, that is the number of atoms in the excited level should be more than the number of atoms in the ground level. That is called population inversion. That word you might have heard about when you just study about lasers. That is, you may have an active medium, either it could be solid or gas, and you have to excite the atoms from the ground level to the excited level. So at one point, the number of atoms in the excited level should be more than the number of atoms in the ground level. So that is called population inversion, inverted population. So then only if any photon can stimulate an atom in the excited level to go to the ground level. So if you have more number of photons, then more number of atoms will go to the ground level. So more number of photons will be produced. So the amplification, will happen. Unless you have, the population inversion, you cannot get the amplification. So that's what. So in order to avoid that problem, people started thinking about 3 level and 4 level. So that's what given here. So if you just see in the 3 level process in the animation, so it is just, the atom is excited from the ground state to the E3, that is a short-lived state. And from that, it will go to the metastable state, because the lifetime of atoms in the metastable state will be slightly higher than the lifetime of atoms in the excited level E3. So if this is possible, then it's very easy to produce the population inversion between this E2 and E1. So when the population is produced between E2 and E1, you can see that stimulated emission possible and laser emission takes place. But here also there is a problem, because the lower laser level, that is the ground level, is the lower laser level. So that means in order to achieve the population inversion, more than half of the atoms should be excited to the short-lived state, and then it will come to the metastable state. Then only the population inversion can take place. So in this case, the efficiency is very less, but our Ruby laser comes under this category. But in order to avoid this, we have another system called 4-level system. So in the case of 4-level system, you can see that like example is helium neon laser. So the helium atoms are excited to the exciter level, and from this actually there is an energy transfer takes place to neon, and this neon atoms also excited to the level E2, and from E2 to E1 it will come back to this level, and from this actually the laser emission takes place when it comes to the from E2 to E3. So that's what the laser comes. So you can understand with this 4-level system, if you see the schematic, you will understand easily. So in the schematic, how the population inversion is achieved, even this lower laser level is almost empty. Even one atom in the upper laser level can create a population inversion between these two states, because the ground state is different. Okay, so the population inversion is very simple in the case of 4-level system. So the efficiency of this system is very high when compared to this 3-level system. So this is what actually some of the gas lasers, typical example is a helium neon laser, which comes, the wavelength is 693.8 nanometer is the wavelength. This is in red region. Okay, so this is these are the two types of lasers actually. One is 3-level system. In all the laser, either it should belong to 3-level laser system, or it should belong to 4-level laser system. Okay, then the next. Okay, we have laser system, and how this the process will continue and how you will get an output. That's what here it is mentioned. It is like a simple oscillator in electronics. If you see, you know what is amplifier in electronics. Okay, so in the case of amplifier, you can convert that amplifier into an oscillator by taking the output and fed back to the input. So that way you can convert an amplifier into oscillator. So this is the same analogy you can apply for laser system also. So you see here active medium, it could be either solid or liquid or gas. And this is excitation mechanism, so that the atoms will go to the exciter level. And also, the stimulated process, emission process will take place. And the photons produced by the simulated emission process will be coming out. And when it comes out, you see there are two mirrors. So one is 100% reflection, the other one is slightly less than 100%. So what will happen is these photons are started oscillating between these mirrors. So once it is getting reflected from the mirror 100%, then again this photon will go to the active medium, and what will happen is it will stimulate more number of atoms to go to the ground level, and it will come here, because this mirror, the other mirror, the rear side mirror is less than 100%. So a part of the photons are coming out as a laser beam. So in this way, the laser beam, that is the photons, the stimulated photons can be made oscillating between these two mirrors, so that the entire population inversion, the entire atoms in the exciter level can be made to go to the ground level, and simultaneously the excitation mechanism also there. So this process will continue, and you will get a continuous output of laser. So this is what laser oscillator. Actually, initially it was actually coined as LOSER, LOSER, because laser oscillation by stimulated emission of radiation. But that word is not up for getting funding and other things. So what they have just modified that oscillator into amplification, laser amplification, light amplification by stimulated emission of radiation. Okay, right. So next. So these are the components, as I told you, active medium. So active medium could be solid or semiconductor or gas or liquid. and dyes. So anything could be. So there are some typical things I have given to you, and there are excitation source that could be flash lamps, electrical discharge, and that leads to population inversion, and then this resonator which makes this oscillation and all. So this is what the components of lasers. So I hope now you have a fairly good idea about how this stimulation, how this laser takes place, laser emits, the laser emission takes place. You have a good idea about it. And there are types of lasers. There are, because based on the active medium. So in the case of solid state laser, the active medium is solid. So in the case of ruby laser, there is a ruby rod, ND-ag laser, and holmium ag laser, erbium ag laser, and distributed feedback, some system DPSS, and ytterbium laser. And gas lasers, the active medium is gas, because CO2 laser, argon fluoride, krypton fluoride, xenon chloride. These in bracket, the wavelengths are given. And there are liquid lasers. Even organic dyes can be useful. Even laser shows and all, they are using these liquid lasers for laser shows. Okay, so these are the various types of lasers that people are using for research and for other applications also. So now, how these lasers can be useful for applications, because the main objective is how these lasers can be useful for several applications. So in order to understand the applications, we need to understand the characteristics of lasers. Okay, so there are 4 characteristics you can see. Monochromatic, monochromatic means single frequency, single wavelength. So you know that in the stimulated emission process, as I said earlier, the photons emitted, all the photons emitted are in phase with each other, all are having the same wavelength. So automatically it is monochromatic. And then coherent. So all the photons emitted during stimulated emission all are in phase with each other. I will explain what is coherence. So there are 2 types of coherence, spatial and temporal. Each is having separate application. That is why I put these 2 types. And then highly directional. Directional means if you just compare a torchlight, and if you just switch on the torchlight and you see the beam after 1 meter, the beam is actually expanded like anything. But in the case of laser, even you might have seen laser pointer, so it won't actually diverge. So the divergence is very limited. That's what less divergent, and high brightness. So the bright, because it has monochromatic and coherent and highly directional. So if you focus that, it will be, the number of photons at the focused spot will be very high. So that is, intensity will be very high. That is why you can't see the laser directly. So it will just be focused by your eye lens to the retina, and retina will be burned out. Okay, so that is why we have to have protective measures for this laser to prevent damage, eye damage from the laser. So these are the 4 main characteristics. Okay, so if you see here, the characteristics, first one is ordinary light. So you can see ordinary light having several wavelengths. It is not necessarily a monochromatic, because it is, many wavelengths. For white light, if you take, there are 7 colors. And the next picture shows there is incoherent, but monochromatic. You see the waves, to understand how it is. So these waves are not in phase with each other. So that means even though it is monochromatic, single color, but it is incoherent. But the third one, if you see, all waves are coherent. This is what called coherent and also monochromatic. So lasers are coherent and also monochromatic. Okay. So, and this is actually to understand how these 2 types of coherence, spatial and temporal. You see the first one, coherent, that we have seen already in the last case. But in the case of spatial coherent, you see that there are waves. Okay, so these waves are in space. These 4 waves are coherent spatially. But temporally, if you see, temporal means with respect to time. So after certain time, there is a discontinuity in these waves. That means these waves are incoherent after certain time. So it will travel from this point to this point. And then what happens is actually at this point, it is getting, changed. The phase will be changed. So that means it is having only partially temporal coherent. Okay, so that's what spatially means. It is spatially coherent, but the temporal coherence is very, temporal means with respect to time. Spatial means with respect to the area. Okay, that's what the 2 things. And the last one is incoherent. Incoherent means you see the random waves are random phase, they are not in phase with each other. So these are called incoherent. This is just to understand how spatial and temporal coherence means. So now, in order to understand in a much better way, you see the coherence, the soldiers march fast. You can see this is called coherence. And you see incoherence, the people are in random direction and they are not at all in coherent way. And this is a partial coherence. You can see that there are some, people are following something, but there are some people are not following this rows. So this is a partial coherence. These are just to understand what do you mean by coherence. Okay. Right. The next one is directionality. As I told you, this first one is a torchlight. You can see that if you just switch on the torchlight, for typically 2 kilometer torchlight or some other flashlight, you can see, it will just the divergence is much higher. So it will also, the size is 2 kilometer. But in the case of laser, you can see that the divergence, it can be measured in terms of radians. So you see that it is 10 raised to minus 5 radians. That is 2 seconds of arc. It is also limited by diffraction. We don't need to go into the details of that. But this laser is actually very, very high, means highly directional. Okay, that's what we have to understand. So because it is having a highly directional, so you can see that it can be able to focus. If you see this, F number of proper F number, and if you could able to focus this laser, and so this is actually a photograph of that laser focused by a lens. So you can see that there is a spark produced in air because the air molecules will be ionized, because at the focus spot, the electric field is of 10 raised to 9 volt per meter. You can understand how much, the intense because of this directionality. So this is what another property. This can be useful for materials processing and other applications. So the third one is brightness. So you can see, the simple thing as I told. So we have taken a helium neon laser here. So it is 632.8 nanometer and 1 milliwatt power, because the laser output which can be measured in terms of power, because there is a continuously output is coming. So it can be measured in terms of power, energy per second. So the spot size is 1 millimeter and the divergence is 0.5 milliradian. So if you calculate, the brightness is around 1.62 into 10 raised to 9 watt per meter square per stereo. So this is what the brightness produced by a helium neon laser of 1 milliwatt. You can see, if you could able to calculate by Stephen's law, the brightness of sun, it is actually 5.9 into 10 raised to 6 watt per meter square per stereo. So if you just compare, the brightness of laser is 300 times of the sun. So that is the, that is the reason we are saying you cannot look the laser directly, because it will definitely damage your retina. Okay, right. So, and in addition, there are 2 ways, 2 possibilities, 2 outputs, 2 types of outputs from laser. One is continuous output, the other one is pulsed output, like flashlight. So because in the continuous output, it is very difficult to produce lasers of high energy, high power. It is very difficult because you have to have a huge active medium, and we have to spend a lot of money for that. Because to have a ruby rod very high, size of some 10 centimeter itself, it is of a huge cost. You have to spend a lot of money for that. So in order to avoid that, you can go for pulse laser. So the laser will come in terms of pulses. So the pulses can be, the energy is actually energy per pulse you can measure. So if you see that the peak power in the case of pulse laser, it can be measured by energy per pulse divided by the pulse width. So depending on the pulse width, the peak power could vary. So whatever you are achieving with continuously output laser, you can achieve with the pulse laser quickly. So that is the advantage of that laser output. Actually, this is pulsed as well as continuous. Then you can see the laser wavelengths. It is almost from ultraviolet to infrared. You can produce lasers, actually the various types of lasers. This is listed out here. So you can see how, you can, now that we have technology to produce lasers in almost all the wavelengths, actually, used for several applications. So now, there are some classifications, because there are some signboards also we have to measure, means to take protective measures in order to, when you go for lab having lasers and all. So you can see there are lasers categorized as class 1. So you can just, it is safe and it will not produce any injury, and it's low level, and label is not required. So for example, lasers like your barcode readers, and so there are lasers. There are also semiconductor lasers. They are semiconductor lasers. So you don't need to have any, because it is very low. So those lasers are coming under class 1 category. And then class 2. The class 2, because these are based on the level of radiation, that is the power level, how the power level we can classify. So if the power is maximum CW 1 milliwatt, it comes under class 2 category. So class 2 category, then you have to have this kind of call, notice warning symbol, actually class 2 laser product. So you can just see helium neon laser coming under this category. These are some, warning signs for people, so that they will have to wear some protective glasses actually. And then there are other 2 classes. Class 3A, that is actually maximum power is 5 milliwatt. So you can see even the laser pointer and all that comes under that category. So it is you have to be careful actually when you are using the CW laser with having 5 milliwatt power. So the symbol for using this kind of lasers is this one. This is class 3A, and then there are class 3B. It comes under 500 milliwatt, and then class 4. It is actually, it is still higher. So you can see that what kind of warning symbols you have to use, because you see the person is wearing some goggles, so that to protect your eyewears, so that you can avoid from eye injury and all. So these are some classifications that worldwide people are using. So even though if you have any qualification, when you go and use lasers, you have to pass certain courses, safety courses, unless otherwise you cannot allow, you cannot be allowed to enter the laser laboratory. So it is like that only. So see, these are some safety requirements whenever you visit any laboratory in abroad or in India. So these are the safety, when you open the laser, there will be some safety interlocks will be there, and it will automatically terminate the laser system, and then warning symbols, and all those things will be. These are some standard procedure for laser laboratory. These are some standard warning symbols which I showed earlier for different classes. So these are international laser warning labels. So wherever you see, when you go to some laboratory or some places where they are using laser, you can find these kind of warning symbols. Okay. And this is another controlled area warning signs for class 4 laser actually. So these are different warning symbols. And then there are protective equipment, PPE, personal protective equipment for eyes actually. What type of, because this eyewear, goggles, it is not of same type. Actually, this eyewear will be different for different, you have to use different lasers. So how it is actually, it is based on the optical density, and also this MPE means maximum permissible exposure level. So all these things, with using all these things, you can able to select which laser, means which type of the eyewear you can able to use. That depends on the wavelength compatibility and all those things. You can't use for helium neon laser, whatever you are using, you cannot use for infrared or ultraviolet laser. You have to change that. So these are also standard procedure is there. So the next one is type of laser. So in the type of laser, I am just, I explained only the ruby laser, actually that was developed by Mayman in 1960. So you can see that the lasing medium is ruby rod. It is a solid state actually laser, because the ruby rod is a solid material. So 2 to 20 centimeters, that depending on the type of laser, what you are using. So you can see the ruby rod consists of, it is a matrix of aluminum oxide, in which aluminum ions replaced by chromium ions actually. So how is that details are there. And it is a 3-level laser, which I mentioned earlier. So the lasing action takes place between the energy levels of chromium ions. So this aluminum oxide used as actually to excite the chromium ions actually. So pumping of chromium ions that is happened by flash lamp actually. So there is a kind of xenon or krypton flash lamp can be useful for exciting the ions, chromium ions to higher energy level. And what is actually the absorbing the wavelength? You can see here 5,500 angstrom to 4,000 angstrom, and it is levels E1 to E2. Okay, so these are the wavelengths required to excite the atoms to levels E1 and E2. Okay, so these are the simple energy level diagram for a ruby laser. So it will be excited due to pump radiations. It will be excited to E1 and E2. The atoms from E1 and E2 both will very fast. It will come to the level M, this metastable level. So this is very fast and non-radiative transition. Okay, that's what I told. It is need not be photons. It could be due to some heat radiation also. So from this, this in bracket, it is given the lifetime of atoms in this. So you can see that the lifetime of atoms in the metastable level is slightly more than the lifetime of atoms in the pumping level. So from this metastable to ground level, there is a lasing action takes place. So these are simple energy level diagram of ruby laser. And this is actually how this setup actually ruby laser. So you can see the flash lamp is around this ruby rod, and these are two mirrors. That is resonator, what I told. And this resonator is actually, you can see this is a type of elliptical configuration. So it is a cross-sectional view of that. So in one foci, you have this flash lamp, and the another foci, you have ruby rod. And according to the property of ellipse, whatever the radiation coming from this flash lamp, after reflection, it will reach the ruby rod. That is for efficient excitation. These type of elliptical reflectors could be useful. Okay, this is what the configuration of ruby laser. Then coming to the point of applications, I hope at this point you have a good idea about lasers and how lasers are produced and what are the characteristics of lasers. And so now with this idea, we can just see what are the applications. So there are these applications is based on how this laser will interact with the material. So you can see the famous scientist von Neumann. He stated that once the lasers were invented, they simply had to be used in material science, because almost for all the research, people are using now lasers one way or other. Without lasers, there is no material science research. That's what actually nowadays at present. So you can see the list: applications, medicine, industry, defense, research, and commercial. So in each category, how it is useful. So you can just see that medicine, you have blood laser surgery, laser healing, laser therapy, and photoacoustic imaging. We are going to see that. And in the case of industry, cutting, welding, and bending also there, and heat treatment of materials. And then defense, marking targets, missile guiding, and even as the snipers, you can see the laser pointer will be there to get the target. And there are a lot of applications. Of course, in research, there are several ways we can use lasers in research. And commercial applications in our day-to-day life, you can see laser printers and CDs, barcode scanners, CD writing, CD reading, and also holograms. Okay, so these are some of the applications. I have not listed everything, but some of the applications I have listed here. Then all these applications, as I told, how this laser interacts with the material. Okay, so this is actually, there are 2-3 types of interaction. One is photothermal. Photothermal means these photons, laser photons, will create some thermal reaction with the materials. Okay, so that is actually melting. You know that when you heat a material, when you just shine a material with lasers, first it will be heated, and if you just increase the power of the laser, then it will go to melting, and then it will go to fabrication, and then plasma formation. So these are the sequence takes place that comes under photothermal. And then photomechanical. Suppose once the material is melted, then what will happen? These photons having high energy, it will have high pressure, so that the molten material can be expelled from the from the area of the irradiated area. So that is called photomechanical. And the other one is actually photochemical. Photochemical means some of the biological samples. Suppose, for example, LASIK surgery. Those things are organic, that is biological samples. So the incident laser beam, if it is equivalent to the bond energy, for example, OH bond, 4.8 electron volt, and NH bond, 4.1 electron. So the incoming lasers, that is, for example, UV laser, you can see the UV laser, argon fluoride, the energy of the photons is actually 6.4 electron volt. So this is higher than the bond energy. So in that case, what will happen if you radiate the molecular organic molecules, then what will happen? These molecular bonds will be disrupted by the energy of these photons. Okay, so that means the photons break chemical bonds in molecules of organic materials. So these are the three categories of interaction takes place when laser falls on a material. That is photothermal, photochemical, and photomechanical. Okay. Then in the case of medicine, what are the applications? You can see there are several applications I listed. I will just go, one of the very good application. So there are low level therapy and to 10 milliwatt to 200 milliwatt and low intensity laser therapy. So it will generate some heat and initiate chemical change and disrupt molecular bonds and produce free radicals. I will show some of the things in medicine. So you can see biostimulation, for example. In the case of biostimulation, the energy from laser radiation, it stimulates the biological functions of cells and then tissue so that it can just improve the the vitality of that is regenerate the cells again, so that the cells will be again from the dead cells can be triggered and it can be live again. So this application, this biostimulation is nothing but live stimulation. So you can see here, this is a schematic showing actually how these photons stimulate the cells. So you can see how the increased vitality will result. So you can see here, so for example, skin regeneration. So you can see how before laser and treatment and after laser treatment, the wrinkles in the face can be treated, and some scars in the skin can be treated, and your skin will be it will look nice and it will look young. You will look younger, and all those things are commercially nowadays available. It's called skin regeneration. So this is another way, how to shape actually. This is another application before and after. You can see how your face, the particular area can be shaped. So that is also possible using biostimulation. This is one of the famous applications. And then you can see the LASIK surgery. You can see how the lasers can be useful. So that first, the laser, you can use some knife to remove the first one, the flap, and then you can just shine that lens by using some laser radiation to reduce the thickness of the lens, so that it can be short-sighted or long-sighted can be corrected by just ablating, that is removing some material, some lens material, so that it can be corrected. That's what here. So this is explained in schematic like this. So what is the first thing? Corneal flap is created with a microkeratome, and then the corneal flap is the next one is folded back, so that you can use laser to shape the lens cornea, and then again the corneal flap is folded back in place. So this is what your LASIK surgery is, photoablation. And then the next one is photoacoustic imaging. This is a very interesting application you can see. So you can see the schematic here. So if you have, this is a non-invasive way to find, suppose if you have some tumor somewhere in the body, you don't need to have some scanners that will touch your body. So you can use laser without touching. You can able to understand what is actually, where is the tumor. So that's what here. So that portion is irradiated by laser. You can see here. And because of the heating, it will produce ultrasonic waves, US waves. And these ultrasonic waves will be captured by this transducer, and it can be amplified. and using a data acquisition system, and it will be converted into acoustic image. Okay, so this is the way this photoacoustic imaging can be useful in several ways to understand what is there, what is the problem. Even the child in mother's womb. So you can able to understand whether the child is okay or not, or everything you can able to find out. This is what you can see here in this picture. So this is actually taken by photoacoustic imaging, and also here you can see the schematic how this tumor can be identified by using this laser assisted photoacoustic imaging. So this is how the lasers can be useful for acoustic imaging. These are developed recently in 2018 and 19 and all. So using pulse lasers, as I mentioned, the output laser pulses, this can be effectively, it can be done. You don't need to touch the patient, because it will give some discomfort for the patients. So without discomfort, you can do the analysis that is called non-invasive. Actually, you don't need to touch, or without disturbing the patient, you can able to analyze, and you can find out where is this tumor and all. Okay, this is called photoacoustic imaging. Then lasers can be useful very much for communication purpose. So in the communication, that nowadays fiber optic communication, mainly they are using lasers. So that when compared to the communication before 20 years and now, we have no cell phones and all at that time, because here, even in Amrita, we have from one campus, means one building to another building, we have fiber optic cables, so that the data can be communicated through lasers actually, because there are a lot of advantages in lasers, because there is no electromagnetic disturbance if you are using lasers. And another way is it will not be disrupted by any earthquake or even in a cyclone and all. Even from Singapore to India, there are undersea fiber optic cables. So the data can be communicated from one place to another place without any disturbance. So that is for communication actually. So you can see, how this communication. So that is the reason nowadays, even, you just see how you can see, I think in home also, people are giving internet connections using fibers directly to home. So you can get the quality, you can get higher bandwidth without any disturbance. Okay, that is the advantage of because of the semiconductor lasers. That is lasers using semiconductor materials. So these are some of the details of that lasers, how it is useful in communication actually. And then the next one is materials processing. Again, as I told you, it is actually based on photothermal, photomechanical, and photochemical. So we will see certain applications, that is hardening. Suppose if you see in an engine of a car or engine of some machine, so there is something called piston. So normally this piston will work, sometimes if the machine is working continuously for 24 hours, only the piston, some certain part of the piston actually continuously it will work. So there will be some wear and tear of that portion. So what people have to do is you have to harden that area surface of that. So that is alter that material only on the surface. So how to do that? So lasers could be possible. So if you just irradiate the portion, then that portion alone will be hardened. And also surface alloying. Surface alloying means you can mix, you can melt that material and mix some other material with that, so that the surface can be hardened and it can be modified. And also cladding. So these are some of the process called surface treatment. So you can see here how the surface treatment can be done. So you can just see here, this is actually some piston thing actually. The steel surface is converted into from austenite to martensite actually. So you can see that how this is done, and the hardness can be increased by just irradiating this laser. This is one type of materials processing. And also surface texturing. So you can texture the surface, even the car industry and all, people are using lasers to texture the surface. And also, if you just texture the surface, it can be useful for several applications actually. For solar cell application. Solar cell means you have to trap more solar radiation on the solar cell. So how to do that? You can just texture the solar cell surface by micro size texturing or nano texturing, so that more light can be trapped.
Sorry, due to the technical issues, we had to wind up. Sorry from our side. Anyway, thank you, sir. Thank you, Sivakumar sir, for such a wonderful session. And thank you all the participants. Thank you so much.